And what has so far been a really fun and interesting conference. So I will start with a vague introduction. And I'm emphasizing the word vague before the war of counterexamples begin. And I will spare you of a lot of technical details, so definitely no phi gamma modulus as well in this talk. So there's this general philosophy in perhaps a Langlands problem that we try to relate algebraic invariance to analytic invariance. And in a lot of the talks so far, we have seen specific manifestations of this. For example, the Bloccata conjecture, which considers pi some nice automorphic representation of some nice reductive group, and we study its p-adic, L function, and perhaps the special values of this complex analytic object we can attach to an automorphic form. And what we would like to do is relate this to perhaps some algebraic invariance of pi. But this general philosophy perhaps is quite difficult to attack directly. So what do we do as number theorists? We fix our favorite prime number p and look at things p-adic. So then Iwasawa theory comes into play. And it predicts that we can replace both sides of this analogy with p-adic versions of them. So on the complex analytic side of the story, we want to construct some p-adic object. Conveniently, we call a p-adic function. And we didn't want to. L P of 5. And we would like to relate this to some sort of p-adic invariance of pi. So we saw, for example, in Ash's talk this morning that doing things from an Iwasawa theoretic point of view can help us tackle big conjectures in the area. And I have been quite vague about what each of this side means, but most of you probably already know that on the algebraic side of conjectures like the Bloccata, we have some sort of Selmer group that we would like to study. And then when we look at things p-adically, Iwasawa theory replaces it with some sort of p-adic Selmer group. But today, I would like to focus on the left-hand side of the analogy, where we want to replace this complex analytic L function with some sort of p-adic object. And hopefully, in similar ways to what David's introduction yesterday explained to us, we would like to plug in some nice enough characters in this p-adic object and see the special values that initially we wanted to study. Great. So a natural question to ask at this point is, for which objects can we construct this p-adic functions? And today, I want to focus on a specific case of groups, which I will call spherical. First, so what are these groups? So a pair G, H of some reductive groups, where H will be a subgroup G, is called spherical if B, which is some sort of Borel of G, has an open and then sorbet in G mod H. Now, this definition is a little bit technical, and if you haven't seen it before, it's kind of hard to start thinking of examples. But the slogan is that H is big in G. Right. So, of course, G is big in G. It's all of a G. But we can have better examples that can actually be useful for our object, which is to construct p-adic functions. So we'll give some examples that fall under the category of this. Right, so the first is consider GL2 times GL2 times GL2. Now, this has appeared already today, but consider GL2 as a subgroup of this triple product where we take G and we send it to G, comma G, comma G. So just the diagonal embedding of GL2. It turns out that even though you think of GL2 inside a triple product of GL2s as small, it's big enough for our purposes. Another example is GL2n, so the 2n by 2n matrices, and the subgroup we will consider is GLN times GLN. So the way we embed this is we take a matrix G and a matrix H, and we send it to the 2n by 2n matrix where we put G on the top left corner and H on the bottom. And the third example that I want to give has been spoiled by the title, is a product of unitary groups. So we take UN plus 1 times UN, and the subgroup we consider is UN, where we take G, an element of UN, and we embed it also kind of diagonally on the UN component. It just stays as itself, and then on the UN plus 1 component, we embed it in the n plus 1 times n plus 1 matrix with G on the top left corner, and then just 1. Right. So hopefully everyone can see this. So why are these spherical pairs interesting? And for the purposes of this talk, these specific spherical pairs are interesting because they fall under this big kind of set of conjectures by Sakellarides and Venkatesh. Which practically, under the philosophy of their conjectures, when we want to study, say, for some GH spherical and pi, some nice automorphic representation of G, and again, G and H will be a nice spherical pair. When we want to study, say, the center L value of the L function attached to pi, instead of looking at this directly, we could instead look at a specific element phi in pi and look at the integral of it. But instead of looking at all the G points of it, we look at the H points, or maybe almost all of the H points. So now perhaps the slogan of H being big in G has a better manifestation, because I want to study the central L value of an automorphic representation attached to all of G, And it might be enough to just study the H points of an automorphic form of it. And why should one consider this? Is because the right-hand side here might be easier to p-adically interpolate versus directly trying to p-adically interpolate the complex cell function. And the examples that I gave here are not random spherical pairs, but they're spherical pairs where we have manifestations of this philosophy in specific cases. So in the GL2 times GL2 times GL2 case, where we diagonally embed GL2 inside, we have something known as Icino's formula. So now when you take the triple product of some appropriate modular forms, you can study the right-hand side instead of the central L value directly and get a p-adical function. So in this case, Greenberg and Seveso constructed a p-adical function, and more recently, Dalava and Horawa did as well. And I'm sure we'll hear more about this on Friday. So in the GL2N case, again, we have perhaps not an exact replica of Icino's formula in this case, but we have something similar. We have something called Shalaika models for some nice representations. And in this case, again, people in this room, Daniel, Laden, Andy, with their collaborator, Georgia and Williams. Sorry, Chris, I hope I didn't get any of them. They constructed a p-adical function attached to appropriate automorphic representations of GL2N. So the final case is the product of unitary groups. And in this case, we have actually something quite similar to Icino's formula. We have a direct relation of the between the central L value and the square of this object here, which is called an automorphic period integral. And this is known as the Gann-Gross-Prasad conjecture. Which, luckily for me, it's no longer a conjecture. It's a theorem, but we still call it a conjecture because it was recently proven. Anyway, using this conjecture, one can construct a p-adical function and interpolate central L values. So the plan for now is to explain to you what this conjecture tells us and how one can construct a p-adical function using it. Are there any questions? So to state some main results, we do need some notation. So let E be an imaginary quadratic field. And since we construct the p-adical functions, we fix P a prime number that splits in E. And we denote by capital P, which looks a bit like P, but hopefully there won't be any confusions. It comes to formulas. These are the primes above P. Right. So let's define the unitary groups. I'm not hiding anything. So let Vn plus 1 be the Hermitian space of dimension n+1, and we consider the unitary group U of Vn+1, which we denote by Un+1. And Vn, a Hermitian space of codimension 1, which gives us U of Vn, U of n+1, and we impose the condition that these are infinite. So we let G be U n+1 times Un, and the spherical subgroup is U1. The embedding, it's still there, but it's just rated. We take G, we embed it on G, and then G1. Right. So the spherical pair we consider is G and H. And we now need to consider pi some automorphic representation of G. So it will be pi n+1 on the Un+1 component, pi n.
N at least.
Sure.
N=1 should work, surely.
And n+1 is at least 2, and is at least 1, yeah. So Un times U2 is fine.
N=1 is okay, like the Borel is dense in GL2. You're saying U1 plus U2 is spherical? Your definition.
U1 times U2 with this, the subgroup U1 embedded in U1 times U2 is spherical.
By dense, you mean the risky dense?
Yeah. I can't say counterexample, reason why it wouldn't be true from the top of my head, but
GM's density 1.
Is not dense in U2. Yeah, it depends what you put as a Borel in it.
okay, maybe we can circle back to that.
It's a question of convention. Okay.
Yeah. Right, so where were we? So we want to construct p-adic functions, so we need some appropriate automorphic representation. So let pi be a cohomological, cuspidal, irreducible, automorphic representation of G. And we will fix a couple more conditions. We want it to be Iwahori spherical, and a local condition that the home space of pi V is non-zero for all places V.
There's some condition like conjugate self-dual. GGP, at least like for the GGP formulas, there is a condition usually conjugate self-dual.
Yeah, so if you consider the representation that comes from GLN, and then you base change it to some sort of unitary group, then the representation that comes from GLN, you would impose that condition, yeah. But I'm kind of just starting from the unitary group, right?
Logical and cuspidal are actually automatic for a definite group, aren't they? And everything's cuspidal because there aren't any cusps.
Sure. Sure. Right. So for some phi in pi, we would like to study the automorphic period integral, which we define as pi h of phi, and it's the integral of phi h. H, and I said we take h, the integral against h, but we have to quotient out by a few things. So we quotient out by H of Q and ZH of the adults. This is the center of G intersecting H of H. Great. So now what? No. So now we're ready to state GGP conjecture.
You mean low places it has at most Iwahori level or just
At P, I want Iwahori level. Thank you. Right, so we have theorem. Conjecture. And this is due to works of many people over many years. The last two papers where it's proved in generality are due to Plessis, Soduar and Zidor, and Plessis, Liu, Zhang, and Zhu. And it says the following. It says that the following two conditions are equivalent. One, that the automorphic period integral doesn't vanish for some phi in pi. And two, that the central L value is non-zero and that when we take pi and we restrict it to H, this space is non-zero. But
Moment, the first one, I mean, is that true for all phi and
No.
pi, or it exists?
for some, thank you, pi in pi. So the automorphic period integral doesn't vanish identically.
do you take?
So you base change pi to some GLN and then you take that. So in particular,
Hold on, that home space is just the
Sure.
product of those home spaces which you've already assumed is not.
sure, for the purposes of this talk, this is automatic, but in more general GGP versions, you do have this condition, which is why. So in particular, we have a specific and explicit description of the central value in terms of the automorphic period integral. We have that. This square of the automorphic period integral is equal to a long formula, which I will first write, then explain. So we have that the square of the automorphic period integral is equal to some constant that I will explain what it is, times the central L value divided by some adjoint L values, and then some correction factors at a finite number of bad places. So we can put here, delta is a product of abelian values. So we take I from 1 to n+1 of L, I, eta, where eta is the quadratic character from E to Q, to the power of I. SP is the size of the Arthur parameter. And the alpha V's are certain matrix coefficients. So in particular, if we are in the case where this automorphic period integral doesn't vanish identically, there is a specific choice of phi that we can plug in to this side so that this doesn't vanish. And then if this doesn't vanish, we have a specific choice of the local phi v's such that these matrix coefficients are explicitly computable and we can view this as a constant.
Sorry, what's delta?
Sorry, yeah, this is not written very nicely, but it's a product of L values where eta is the quadratic character from E to Q to some power I evaluated at I. From 1 to n+1. So, yeah. This formula, though, it can also see twists by anticyclotomic characters. So we want to twist by characters that come from here. So we want to consider characters that come from here, but we don't want to see the characters that come from Q. Which are characters that come here. So we just consider the natural map here. We take its kernel. And we call this gamma. And now what we want to do is we want to twist by characters chi of gamma. And to do that, we don't change much. We twist the automorphic period integral by this. And then the statement here is what one would expect. We twist the automorphic period integral, and then we twist the central value, and you twist appropriately the matrix coefficients, but again, not much change. Great. So we can now state main result. So fix L of QP a finite extension, large enough. Extension. Fix pi tilde, which is pi alpha p, a non-critical slope. Here refinement of our automorphic representation pi. This is just some choice of UP eigenvalue.
Xenia, what was capital P?
Capital P are just the primes above P. Yes, thank you.
Yeah, okay,
Thank
thanks,
you,
yeah.
Yeah. So we fix a non-critical P refinement of pi. So because the cohomological weight has 2n+1 components, I'm not going to write down the explicit formula of what this means, but it's a condition that comes directly from the weight. If you just keep in mind what you saw yesterday in David's talk, where we had some sort of upper bound by k-1, where k was the weight of modular form, you don't lose much intuition. And now one thing is that I won't just twist by characters of finite order, but we will twist by characters which we will call accessible. If it's of infinity type j minus j, where, sorry, I will hide this for just a second. Yeah, so we take characters of infinity type j minus j, where j belongs to some set of critical integers for pi. This is why I put definition in quotations. So again, David Stock yesterday did me a big favor because it gives you enough intuition. The characters j were going up to k minus 1. So this is just a finite subset of z. Excellent. So, where should I erase? There. The theorem. Is as follows. There exists a distribution which I call L pi or P in the space of distributions from gamma. Well, where gamma is this group here and L is the finite extension that we fixed of growth UP alpha P such that for all accessible characters pi of conductor P to the C, where C is some positive, something positive. If we set L pi of chi to be the integral against gamma of chi d LP of pi, this distribution, then practically what we see is the automorphic period integral here, and we therefore have this formula. So we have the central value divided by all functions. And then we have times some sort of constant here, which is explicitly computable, and it depends on some choices of hard measures we make along the way. The choice of peer refinement and the conductor of chi.
Archimedean square, absolute value square.
Yeah, so you kind of like embed this into C and then you take the square.
One also expect an actual square inside, like maybe there are various expectations. one expectation is what you wrote, another expectation is this actually an element in the equal distribution algebra such that it's square equal. Possibly up to changing the factors like the what is one of alpha.
Possibly, yeah. And in particular, if the slope of the P refinement that we have chosen is small enough, in particular, if it's smaller than the size of this crit pi that I did not define there, then this interpolation formula,
So UP of alpha P is p-adic valuation.
The VP.
yeah,
But what is alpha p? I mean, is it a number or is it some more complicated thing?
alpha P, this is, maybe we can make this AP. It's the choice of P refinement.
Right. But a p refinement is a character of some torus of rank 2n+1. So it's 2n
This
plus
is
1 numbers.
You can think of this as a number, a specific eigenvalue that is a number that I can compute. It's p-adic valuation. So the above interpolation formula, in the case where the slope is small enough, determines the p-adic L function uniquely.
So in the beginning, you assumed that prime P is split.
Sorry, I didn't hear you.
At the beginning, you assumed that prime P is split in E. How necessary is that?
It's very necessary. Yeah, it's very necessary in computing the extra fudge factors that you get on this side here.
So you believe that you still can construct something in the other case? Because in the GL2 times GL1 case, this is
Yeah, I don't know the answer to how one would do that.
So
Would comp-
Andreetta and Iovita, we don't even know what is the distribution growth. We don't Even in the ordinary case, I mean, depends on the interpolation region.
You also have an algebraicity statement.
Yeah, this is known, it's not proved by me, though.
The thing on the left-hand side is algebraic.
But that comes from the theory of the GGP, the automorphic stuff. I don't have to do that. Okay. So a couple of remarks. The first is that this extends in recent work of Yifeng Liu, who however works in ordinary and trivial cohomological weight case. But he does define it over arbitrary CM extensions. I have no reason, I'm pretty sure that everything can be extended to CM extensions as well. It's just very notation heavy and we would lose intuition. And the second remark is that, so to determine the p-adic L function uniquely here, we need to impose some extra condition on the slope of the representation, which was one of the two expectations to get uniqueness that David mentioned yesterday. And the other one was that if one can extend this to a family, then perhaps you can get uniqueness like that. And it turns out that we can do this sort of thing for a Coleman family through pi tilde. And I will proceed to explain how one does now. Right. Right, so pi is cohomological. So it's cohomological of some weight. Lambda. So lambda generates V lambda at highest weight, lambda representation of G. So in the case that we want to construct a p-adical function, we have that the home space of V lambda V dual L is non-zero. And in particular, in this case, this branching law is multiplicity free. So we know that the dimension of the space is exactly 1, which means that we can fix up to some V lambda dual, sum up from V lambda dual to L, and we call it evaluation lambda. So evaluation lambda is some generator of this line. Excellent.
Doesn't this depend on the critical range?
Yeah, so I assume that practically J is equal to 0 is in the critical range. So you get the branching law here.
Or if 0 is in crit, okay.
Yeah. All right, so this space V lambda is what did I do? It's not too hard to see what it is because we have this wonderful theorem due to Borel. And then Bott, which tells us the following. It tells us that V lambda is isomorphic to the space of functions from G of QP to L, such that F is algebraic and it behaves as follows. For all the elements n bar in the lower unipotent, it does nothing. For the elements of the torus, it does exactly what lambda does. And for all other G, is G, F of G. Right.
QP. QP.
G of QP, yeah.
T of QP.
Q of what?
Use from T of QP or T of ZP?
I think from T of ZP is okay. Now this naturally lives inside this space where we take the functions from the Ihori of G to L that are locally analytic and behave in the same way. So n bar is in n bar intersection Ihori, P is in T, G is in G, sorry, in Ihori, and yeah, they act the same way. So this naturally lives inside this space. So the statement of the theorem, by the way, ends here. So we can dualize this space. We get the lambda 2, and we can dualize this space. And we get a space which we call the lambda. So we get a natural map here. The lambda. What did I call this map? Iota. So let's call this map iota star. And the space of distributions that the p-adic function lives in is the space of distributions from gamma to L. So we want an object that lands in here. And from here down to L, we have a natural map. Say you take mu and you send it to mu of 1. So what we want to do now is to periodically interpolate this evaluation lambda map on the space of distributions and construct a map, let's call it capital evaluation lambda, such that this whole thing here commutes. Great. So why does this give us a p-adic function? So when we consider automorphic forms from pi, these are practically functions that look like this. They go from g of a to v lambda, and then let's say we plug in this evaluation lambda that we have fixed, and we land in L. If we impose enough conditions on our p refinement, which is what non-criticality does exactly, then you can lift this space of functions from g of the adels to v lambda dual to a space of functions, let's call them capital phi, that go from the g of the adels to d lambda. This is what is known as a classicality theorem. So you start with some choice of test vector that the GGP conjecture provides you with. You apply your classicality result and you lift it to capital phi. You put it through the machinery of this p-adic interpolation. And you end up with an element here, LP pi of tilde, such that when you specialize, it's the same as just looking at the automorphic period integral along this function here. So you construct a distribution up here whose specializations give you exactly this formula here. Great. But I promise that we can do this in families, and it's true.
Quickly saying how to define this, how to construct this evaluation lambda.
So if your space is of your space of weights is nice enough, you can write a bunch of basis vectors that generate all these weights that look like lambda. And then the thing that I just erased, which was this condition of when this space of function from here to here is one-dimensional, is an explicit branching law. And you can explicitly find which basis vectors satisfy a condition like this. Write out evaluation lambda in terms of those branching law vectors and show eventually that it is the map that you wanted to construct. So you kind of start pretending you don't know what this should look like, and you cook up the thing that it should be. And once you've written it down explicitly, it's not too complicated to lift it p-adically. You get enough intuition by its exact formula that tells you what it should look like on distribution, on the level of distributions.
So this is for certain specific choices of the maps, of the algebraic maps, little a of lambda, right? It's not that you can choose them all completely arbitrarily and you can still define a family thing that interpolates.
No, I choose something that is nice enough, and then I p-adically interpolate that specific vector. And for the purposes of the p-adical function, you don't need more than that. Right, so we have some time, so we can do this in families.
Pretty like gamma is ZP star, right?
Yes,
So you can give how a function on ZP star, you consider it as a function, right? I mean, like this d lambda, you see it as distributions on what? The unipotent?
which one? This d lambda?
It can be
D
identical.
lambda is the dual of this. So these are like maps from this to L.
But concretely, it's on the unipotent. You can see it as distributions on like copies of ZP, right? Explicitly, no? By Vahori decomposition, right?
Sure, yeah,
So I mean, I don't know this case by heart, but like,
it's very similar to your case.
yeah, but I mean, like, so here, I mean, because that question was asked, so you just have like a distribution on copies of ZP, and you just have to embed ZP star in copies of ZPs, which is not very hard, right? So you just have to do it in the correct manner, but like, I'm just saying because like.
Okay, maybe it's, I'm not claiming that to do this, it's hard.
You don't know the.
Yeah. All right, so families. Right, so let W be the white space. For G. And fix some affinoid omega around the point lambda that we would like to p-adically and to see in families. Right, so this comes equipped with a character. I omega from PGP to omega cross such that when we compose it with specialization, we just get back lambda. So we can replace the space d lambda with you can still see it here. We can replace it with the following space. So we consider alpha omega. Now these are going to be functions that are the O omega equivalent of A lambda. So they'll be from Iwahori to L such that for the elements in n bar intersection Iwahori, again, you do nothing. For the elements of the torus, you act as chi omega, and then it's just f of g. So dualize this.
So you want some local good behavior property, right? These should probably be
Yes.
locally analytic functions.
Yes, I said it, but I didn't write it, I think. I didn't write it there either. Thank you. So we dualize. And we get a space, which we call the omega. So we come back here to this diagram. And we have d omega up here and a natural specialization to lambda up here. And then we have the gamma of omega here, again, a natural specialization to lambda up here. So what we want to do is construct an even on a higher level of distribution map f omega such that this whole thing commutes now. And if one has nice enough conditions that allow you to lift your vectors here to some sort of Coleman family through so phi omega is going to be some Coleman family through pi tilde for nice enough. Right? Then what you get is you start with this phi omega, you plug in this machinery, you end up with some element LP phi omega here, which once you specialize is the p-adic function of the previous theorem. That once you specialize completely all the way down to L, what you get is the interpolation formula of that side here.
Do you check that your distribution has the right growth?
Yes, of course. Of course. So once your distribution has, I'm not really stating concretely anything here. I'm just trying to give some intuition because I am running out of time. Maybe I can write one quick remark. But yeah, before I write the remark, let me just finish my train of thought. So if you can lift your phi to some Coleman family through phi, through pi tilde, and you construct a distribution on this level here, once you specialize on nice enough classical omega elements of omega, then you get the p-adic function that we had here, but this had specific conditions. So the remark, I will conclude, is that once you impose conditions on pi that allow you to lift to a Coleman family through pi tilde, you get a function of growth. The same growth as before, which now is uniquely determined by the interpolation formula let's call it at appropriate non-critical lambda in omega, and run out of time. So I'll just say that practically what I've tried to say here in this remark that I haven't made formal is that if we specialize at appropriate classical weights, then we can get uniqueness of the p-adic function LP phi omega for non-critical slope. We no longer need to impose an even further smaller slope condition. And yeah, that's all I wanted to say. Thank you.